Hello, PyData Global. I am so happy to be speaking with you today. My name is MeganPrice, and I am the Executive Director of the Human Rights Data Analysis Group, or HRDAG. And my job today is to tell you more about our organization and our work. And then I'm going to hand the virtual mic over to my colleague and our wonderful statistician, Maria Gargiulo, who will walk us through some specific examples of multi-label classification motivated by some of the work we do. So without further ado, our organization, again, is called the Human Rights Data Analysis Group, or HRDAG. And we are a nonprofit organization based in San Francisco, California, though we have colleagues and partners around the world. And we are a relatively small team of data scientists, and we partner with human rights advocacy organizations, and we work together to identify arguments or questions that can be strengthened and advanced through a bit of quantitative analysis. And over the years, we have been very fortunate to partner with a wide variety of organizations, large and small. And the way our projects typically work is we bring the scientific and technical expertise, and our partners bring deep field knowledge and expertise, and they can provide that substantive question that they know can advance their advocacy work. And then we'll work together to identify what questions can be answered through quantitative analysis with data they may already have, or we'll identify data that may exist that perhaps we can work together to gain access to, or in some cases, we'll work with them to create a data collection plan and to work on collecting data that then can be analyzed to address their question of interest. But at the end of the day, it's really that partnership that makes our projects go. And so today I just wanted to give you a few examples of the kind of work that we do and the stakes that are involved. And that's really where I want to start, is with this quote from my co-founder and colleague, Dr. Patrick Ball, that is at the heart of all that we do. Because we are a team of data scientists, and we do have a tendency to get down into the technical weeds, and we spend a lot of time worrying about our methodological approaches and whether assumptions are being met and debugging code. But at the end of the day, the reason why we're so focused on those technical details is because we all believe that we have a moral obligation to do the best work that's technically possible so that the victim's story is heard and believed. Because to do otherwise disrespects the victim's suffering. And we really do keep that in mind as the motivation behind all of the technical work that we focus on in our day-to-day work. And so I just want to start by providing an example of how broadly we consider things that may constitute data. In some of our more recent projects, most of our data are typically already digitized. Sometimes they may be digitized in a way that I think of as adversarial. We may have images of tables embedded in a PDF file, that kind of thing. But for our older projects and for some of our legacy projects, data may start as physical pieces of paper with handwriting on them. And this is an example of that. These are border crossing records from the border between Kosovo and Albania. And these were handwritten by the guards stationed at that crossing, who wrote down the names of individuals and family members who crossed over that border, fleeing the violence that was happening in Kosovo at the time. Now, ultimately, these records and other data sources were analyzed by Patrick and his team, and he testified against Slobodan Milosevic at the International Criminal Tribunal for the former Yugoslavia, presenting this pattern of refugee flow across that border into Albania and comparing that pattern with known military actions from the different parties to the conflict, specifically during the 3-month period of the NATO bombing campaign. And so that's the kind of analysis that our team does. And although it's not all that common for us to testify in court cases, that is one of the most visible outcomes of our work. And it is the one that has the most direct line between our analyses and efforts for accountability. So as another example of that, this is again Dr. Patrick Ball testifying, this time in Guatemala, in a case against General Efrain Rios Montt, who was the de facto president of Guatemala in the early 1980s, and who was charged with committing acts of genocide. And the analysis that we presented was a comparison of the relative risk of death for members of the Mayan population as compared to the non-Mayan members of the population in the same geographic regions during the same time period. And what we found was that Mayans had a 5 to 8 times greater risk of death than non-Mayan members of the population. And this pattern of violence is consistent with ethnically targeted violence. It is consistent with acts of genocide. And in fact, when the judges declared their verdict, they said specifically that Patrick's analysis confirms in numerical form what the victim said. And this is really the best that we could hope for. At the best point in our work, it affirms and amplifies the voices of victims. And that is always what we're striving for. We recognize that statistical analysis is but one piece of this puzzle, trying to determine an accurate accounting of what has happened and trying to move toward justice and accountability. And this is really one of the best outcomes that we can have. So to provide just one more example of how broadly we think of data, this is one of my favorite photographs. This is Reed Brody from Human Rights Watch standing quite literally shin deep in piles of paper. These were abandoned records kept by the secret police that ran prisons under Hissène Habré when he was the president of Chad. And these are the records about running those prisons. They were information about the number of people in the prison every day and sort of the entrances and exits of prisoners. And this information was analyzed and presented again by Dr. Patrick Ball in the case against Hissène Habré. And in this case, Patrick is showing the crude mortality rate of individuals in those prisons under Hissène Habré's rule. And in this case, when the judges found their verdict, they said that the findings invalidate the contention of the defense that the detainees were receiving comparable treatment to the usual living conditions of the civilian population. And in this case, Habré was found guilty of crimes against humanity, and he was sentenced to 40 years in prison. So again, our statistical analyses are just one piece of the puzzle. We often say that our happy place is in a footnote or in a technical appendix, but to do the job to strengthen arguments rather than weaken them, those statistics absolutely have to be right. And so one of the ways that we try to ensure the rigor of our analyses is through a very meticulous workflow internally. And we work to keep that self-contained and self-documenting. And this is also the way that we keep all of our work as transparent and reproducible as possible. Many of our projects go on for years and years and years, and they may kind of ebb and flow as political situations change. And so it's vital that we be able to return to our work after perhaps a period of time and get reoriented to what we've done in the past as quickly as possible. And so all of that is what drives this workflow and this pipeline that we maintain internally that Patrick has written up in this blog post called "The Task as a Quantum of Workflow." And so if that sounds like your thing, you can definitely go read more about this on our website. There's also a lot more technical posts. We have a whole tech corner where we keep more technical descriptions with code snippets and really getting into the details of this work. So that's a place where you can read more about some of these examples. But of course, one of the key components to this workflow for us are the open source tools that are available through Python and R, the two languages that we write in the most for data processing and analysis. And so with that, it is my absolute pleasure to pass the virtual mic to Maria, who will walk us through some specific examples of multi-label classification, highlighting some of the tools in the Python language that we're able to use to do that work.
Thank you, Megan, for that introduction to HRDAG's work, and hello, everyone. My name is Maria Gargiulo, and I'm a statistician at the Human Rights Data Analysis Group. I'm excited to be here with you at PyData Global and to tell you more about multi-label classification with human rights data. Before I begin, I'd like to give a little bit of an overview of this talk. The first thing I'm going to talk about are two human rights violation data examples that I'm going to reference throughout the talk. The second will be an overview of multi-label classification. So I'll give both an overview of the algorithm and how it works, as well as how it applies to our two human rights violation data examples. Then I'll go and talk about two Python use cases. This is PyData after all. I'll then go on to talk about some thoughts I have about workflow, mainly things I've learned working on HRDAG. And finally, I'll just summarize the various things we've talked about today. So the first problem I'd like to talk with you about is perpetrator imputation. So in this project, we received a data set of various human rights violations. It contained information about the violations themselves, where and when they happened, what occurred, maybe a kind of free text description of the violation, as well as characteristics of the victims, who they were, how old they were, their sex, their ethnicity, etc. We also may have, in some cases, information about the institutional perpetrator. So this is an armed group rather than an individual. And each violation can be attributable to 0, 1, or more perpetrators. Our goal for this project is for those observations missing perpetrator information to predict who the missing institutional perpetrators might be from this predefined list of potential perpetrators. And remember, these predictions can be for 0, 1, or more of the perpetrators simultaneously. When we go to fit our models, which I'll talk about in a little while, our training data are going to be observations in the data set that were not missing perpetrator information. So these are the ones for which we have a full record. The second project I'm going to kind of ground our discussion in is indexing selectors from chat messages. So these chat messages were taken from the phones of the perpetrators of a serious human rights crime. And a selector in this context is basically a theme. So something that might be contained within the message. So something like refers to violence or coordinating with informers. And each chat message can relate to 0, 1, or more selectors. We'd like to find the chat messages that are most interesting to analysts in the legal discovery process. So they've created this list of terms that would be most interesting to them. And we'd like to predict the selectors that each chat message relates to from this predefined list. Unlike the previous problem, however, this didn't kind of come with its own training data. Instead, a group of individuals hand-labeled a bunch of chat messages as pertaining to each one of these selectors. So yes or no refers to violence, yes or no coordinates with informers, etc. If you're interested in this project, you can learn more from the blog post Indexing Selectors from a Collection of Chat Messages by Patrick Ball and Tarek Shah at the bit.ly link that I put at the bottom of this slide. Okay, so now that we have our two examples of human rights problems we're going to talk about today, I'd like to pause and just go over multi-class versus multi-label classification. Because the names are so similar, I often get them confused. So I thought it would be good just to pause for a second, talk about how they're different, and then move on and focus on multi-label classification. So for multi-class classification, we have a single outcome Y. And our goal is to predict a single class that an observation belongs to from 3 or more classes. So rather than binary classification where we have, say, a 0 or 1, an A or a B, we might have A, B, or C. Which class does this observation pertain to? Multi-label classification, on the other hand, has multiple outcomes, Y1, Y2, Yn, and can be kind of any positive number. And our goal is to predict which of 2 or more classes an observation belongs to. And we have no constraints on the number of classes an observation could be assigned to. So an observation could be both classes 1 and 2, 1, 2, and 5, 4 and 8, it doesn't matter. We have no constraints on that. This will sometimes also be called chain classification. Though that's a phrase I might use throughout this presentation. So know that when I say chain classification, what I really mean is multi-label classification. They're the same thing. So again, multi-class, single outcome, multi-label, multiple outcomes. Visually, I'm a really visual person. So I kind of drew this little diagram to help me. You can think of these black outlines of squares as different observations we might see. On the left-hand side, we have multi-class classification. Each square contains information pertaining to exactly one class. You can be the dark green splat, the yellow circle, or the light green cloud. You can't be more than one of them, though. Multi-label classification, on the other hand, admits really any combination. You can be the dark green splat and the yellow circle. You can be just the light green cloud, and you can be all three. It doesn't matter. We don't have any constraints. Again, for these two projects I'm talking about here, I want to talk only about multi-label classification. So now that we understand the difference, we can sort of put aside multi-class classification for now. Diving a little bit deeper into multi-label classification, before we get into kind of the mechanics of how it works, I'd like to just quickly translate it to the vocabulary of the two examples I'm using here today. In the perpetrator imputation case, each observation is a human rights violation. And we have some covariates X that pertain to both the violation and the victims. Our outcomes, Y1, Y2, Yn, are individual perpetrators of human rights violations. So we have a perpetrator 1, 2, 3, up to however many we have. And any violation can pertain to 0, 1, or more of the perpetrators. So up to all of the perpetrators. Although in the project that I worked on, this was uncommon. We usually only had 3 at max, but it could have been all of them. For the indexing selectors from a chat message, each observation is a chat message. The covariates might be things like message length, time it was sent, and our outcomes, Y1, Y2, Yn, are those different themes that might appear in the chat message. Again, things like refers to violence, coordinating with informers. And a chat message can pertain to 0, 1, or more selectors. Remember, again, the perpetrators and the selectors are from a predefined list. They're not just kind of anything that could exist in the world. In these two examples in particular, I'm going to consider multi-label classification the multi-label classification problems that they result in as sequences of binary classifiers. So we'll have one binary classifier for each perpetrator and each selector. That being said, this is not the only way to think about multi-label classification. Multi-label classification is amenable to all sorts of different models and different data situations. But in this talk and for these two examples, I'm talking mainly about sequences of binary classifiers. Just to give you a little visual of what the data looks like again, this is helpful to me. Our covariates X are things about the victims, the violation that occurred in our perpetrator imputation case, and things about maybe date, message length, some topic models for our selector case. And again, each of our individual outcomes, Yi, refers to an individual perpetrator or a particular selector. I'm going to explain the algorithm visually rather than in a kind of formal written sense. This helps me understand it better. So we're going to consider the particular case where we have 3 outcomes, Y1, Y2, Y3. So this would be the case where we have 3 perpetrators we're interested in or 3 text message selectors. And the goal is to predict Y1, Y2, and Y3. And we're going to do it in a sequence. So in this case, I'm going to consider Y1, Y2, Y3, and I'm going to consider them in that order, 1, 2, 3. So to predict Y1, I'm going to fit my binary classifier using just the covariates X. So fit it with X, get some predictions Yi, and these are the probability that the observation pertains to perpetrator 1 or selector 1, for example. Then after predicting Y1, I'm going to go on and predict Y2. And to predict Y2, I'm going to use the covariates X, as I did in the first pass, plus the predicted probabilities of Yi. So those will become, so my predicted probability of Y2, consider covariates X, and the predicted probabilities Y1. For Y3, I do the same thing. Again, I consider the covariates X, I consider the predicted probabilities of Y1, and I consider the predicted probabilities of Y2. This model is sensitive to the ordering of the predictors. Predicting Y1, Y2, Y3 does not necessarily get you the same results for the individual classifiers as if you predicted in, say, the order y3, y2, y1. So we want to repeat this process, randomly reordering the yi's. In this particular case, we only have 3 factorial or 6 models. So it's possible to enumerate all the models, compute them, and get your different outcomes. But in some cases, it'll be computationally intractable to fit all the models. And in those cases, what you do is you randomly shuffle your outcomes and you select a random subset of the shuffles. Then once you have all these models, rather than just considering one individual probability for each y1, y2, y3, knowing that they are sensitive to the order of prediction, one thing you can do is average over the various probabilities for each observation to get kind of a final average probability from the model. And that's how we do it in these 2 cases. So multi-label classification isn't a super popular modeling approach, or at least it's not implemented really widely in the other programming languages I use, but Python actually makes multi-label classification really easy. So below I have a little example function that is kind of a bare bones I took again from Ball and Shaw's post that you should definitely check out, of how you can really easily train and then fit and then get the average predicted probabilities of a chain classifier. I don't do any model evaluation here for simplicity. Model evaluation is really hard though, and you should definitely always do it. But I really wanted to show you how easy this is and how easy scikit-learn makes it and how exciting it is when you want to kind of pick up a problem like this and just kind of start working on it. Python makes that really easy, unlike a lot of other languages where this isn't a commonly implemented type of model. So I think that's really exciting. So next I want to talk to you kind of a little bit meatier version of the project of this analysis is the fact that robust libraries make it really easy to check custom implementations. So when I was doing this, I kind of had 2 things I wanted to do at the same time. So I wanted to make sure I understood the algorithm. So I wanted to write my own custom version of it to make sure I understood what was going on. And I also wanted to learn a new modeling package in R called Tidy Models. And I have 2 points of verification I need to make sure I do in doing this. I need to make sure I understood the classification algorithm itself. So I did the, predicting y1 with just x, predicting y2 with x, and the predicted probabilities of y1, et cetera, that I did that correctly. And also whether or not the specifics in my code were correct. So those are the 2 things I needed to verify in doing my own implementation. And I picked a very particular scenario to try this in. So I tested it in a scenario where I could enumerate every single model. So just like the 3 factorial case where there are only 6 models, I chose a small problem so that there wasn't any randomness in which chains got selected. And the second thing I did is I used a chain logistic regression rather than random forests or something fancier, again, so that I could control for some of the randomness incurred in fitting those models. So I could make sure that I had something that I could reproduce in Python using this really lovely set of scikit-learn lines of code. And what I did is I wrote my implementation in R, and then I checked it against scikit-learn, the scikit-learn implementation, for example, something similar to what I used here, and I saw if the results were the same. And this was a really useful exercise, and having robust libraries like scikit-learn makes this really easy and really fruitful learning exercise for me. So that was a really exciting way to use this really great robust software and also challenge my understanding of this particular problem and another modeling framework. I'm going to transition now into notes about workflow as we're kind of talking about working back and forth in different programming languages and trying different things. And this is really common in HRDAG's work. It's really common for our pipelines to be written in a combination of Python, R, Julia, maybe some Shell. That's really common, and we like to not be bound by any one particular programming language. One, because different programming languages do different things well, and also because sometimes you just want to try something in a different language, or you need to write something in a language for whatever reason. So working in multiple languages is really common. And there are 2 pieces of software that I really want to highlight that make this super easy. that I really love. So the first is the Apache Parquet file type. So if you're a Python user, the PyArrow library will get you this. This is the Arrow library for R. And I really like Parquet files. They're fast, they're compressed, they do all these great performance things, but I really like their ability to make data really easily interoperable and super portable. And this is especially important when data has missingness, which is virtually every single data set HRDAG receives has a lot of missing data. And some other file types really struggle to represent and pass missing data across platforms, but Parquet makes that really easy. And the second thing I'd like to highlight are makefiles. Make is an old tool, but make helps us with pretty much every task I do involves a makefile. And make allows us to execute tasks containing code in different languages with ease. So this relates back to the Python and R question or utilization. It's really easy to write a makefile that runs something in Python, feeds those results into R, maybe then feeds those results into Julia. It's no problem. You just write a rule for whatever script you'd like to run, and it's really easy. But another thing that I'd be remiss not to mention while I'm talking about projects done at HRDAG would be the HRDAG workflow and our core concepts particularly. So HRDAG's 4 core concepts are transparency, auditability, scalability, and reproducibility. These are really important because the problems that HRDAG works on are really high stakes. Human rights is a high stakes environment, so it's really important that we do these 4 things so that our analyses can be robust and kind of stand the test of time. Going a little bit more into depth about these 4 processes, I'd like to start with transparency. So transparency means that code is easy to understand, both like now in the moment in writing it and in 6 months, 2 years, 5 years later when you're trying to go back to it and see what you've done. There's often a degree of cleverness you try to employ when coding, but in general, we try and stay away from that and use things that are straightforward and easily readable rather than a more clever solution. The second is audibility. Everything we do is written in code, and that code is easy to test. There's a full audit trail from start to finish of every single thing we've done, and it's modular in a way that makes it easy to, if you're interested in the results of one particular piece of the analysis, it's easy to kind of pull apart the pipeline and examine just that one thing, which makes it really easy, or I guess easier to isolate bugs and test different pieces when you need to. The third principle is scalability. So I think of scalability kind of in 2 ways. There's the traditional, we try and be modular so that things can be parallelized easily. But I think more important, it's a pipeline that's robust to new data. So if we receive more data for a given project, we can incorporate it without needing to tear everything down and start again. We can just kind of insert, using a makefile, for example, new rules to process the new files and their requisite pieces of the pipeline without too much issue. And the final principle is reproducibility. So to us, that means that as long as someone has, say, the right packages downloaded on their computer, they could rerun any of our analyses from start to finish and get the same results. This is really important to us. In human rights work and really in any stats work, there can't be magic numbers. Results should not just fall out of the sky and then come to exist, but rather be reproducible, and anyone should be able to run that code and understand exactly what you got for your answers. Now I'd like to just summarize briefly what we've talked about today. So first, we saw that the problems of imputing missing perpetrators of human rights violations and predicting chat message themes are 2 problems that are well suited for multi-label classification. We then discussed a little bit more in detail multi-label classification, what it is and how it works. I talked about how Python, and in particular, in my case, scikit-learn made it really easy to run multi-label classification right out of the box without too much startup time. And it made it easy to verify my own custom implementation using a different modeling framework. Finally, Python is an important piece of a larger workflow, of HRDAG's larger workflow, which is grounded in these 4 principles of transparency, auditability, scalability, and reproducibility, which are really essential to human rights violation work. Thanks so much for listening. If you have any questions, you can email me or Megan at our 2 email addresses here. You should definitely follow HRDAG on Twitter, and you can subscribe to our newsletter on the HRDAG website if that's of interest to you. Thanks so much.